Hello and welcome to another edition of Discover Materials Science, brought to you as always from the Madrid Institute of Advanced Studies into Materials Science, or IMDEA Materials. I'm your host, Andrew Johnston. Let's kick things off. In today's edition, we're focusing on some of the fascinating projects being carried out at IMDEA Materials Institute by our Marie Skłodowska-Curie Actions, or MSCA, postdoctoral fellows. The Marie Skłodowska-Curie Actions are the European Union's reference program for doctoral education and postdoctoral training, supporting excellence in research and innovation. To start with, we'll speak with one of IMDEA Materials' newest MSCA postdoctoral fellows, Phuong Vo, who is involved in the M4MID project to develop metal organic framework mixed matrix materials, or MOFs, which are promising candidates to fabricate mixed matrix membranes for gas separation. We'll then hear from Bruno Gomes, a researcher in our Biochemomechanics of Materials research group, who is working on a new treatment for leishmaniasis, an insect-borne disease which is one of the United States Center for Disease Control's most neglected tropical diseases. Finally, we'll speak to Adrian Boccardo, an MSCA postdoctoral fellow who is working to develop patient-customized bone replacement implants, in particular for patients in need of hip replacement procedures. All that to come here in this edition of Discover Materials Science with IMDEA Materials Institute. So let's get this show on the road. So now I'm joined by Phuong Vo. Phuong, I hope I'm pronouncing that correctly.
Perfect.
Now, Phuong, thank you very much, first of all, for joining me on the podcast. Now, you are quite new, not just to anyone who might be listening to us today, but also here at IMDEA Materials Institute, as you've only recently joined us. So first of all, could you just perhaps start by giving us a brief overview of your background and how you came to IMDEA Materials?
Hola, Andrew. Thanks for having me today. My name is Phuong Vo, and I'm a computational chemist. I got my PhD degree in theoretical and computational chemistry from the University of New South Wales in Australia in 2021. Then I did my first postdoc at the University of Sydney before joining IMDEA as a research fellow. So in 2021, I contacted Professor Maciek Harancik, and we decided to write a proposal for Marie Curie Fellowship, and it was granted in the early 2022. So that's how I came.
Great. Now, I understand that your research, Phuong, is focused on exploring the relationships between chemical structures and their properties. Tell me a little bit more about what that involves exactly.
Yeah, it's a bit different with what people often imagine about chemists. We don't work in a chemistry laboratory with chemicals, bakers, instruments, and so on. All of our work is done on computer. Typically, we use high-performance computing cluster. Our main job is to build molecular models to describe the chemical system and their properties. So we use this model to explain experiments and also try to do some tasks which can be very costly and time-consuming to do experimentally.
Now, you've joined IMDEA Materials on a Marie Curie postdoctoral fellowship to work on the M4MID project under the direction of Dr. Maciek Harancik, and which is focused on what are known as metal organic framework mixed matrix materials. Bit of a mouthful there. So I guess my first question here is, what exactly are metal organic framework mixed matrix materials?
Thanks, Andrew. It's very interesting questions. So metal organic framework mixed matrix materials, I call it M4, and nanocomposites comprising synthetic polymer and MOFs as fuels. So since their discovery in 1990s, MOFs have become highly popular materials due to their interesting properties and wide range application, including gas separation, drug delivery, and fire safety products. However, MOFs face several limitations in terms of mechanical flexibility and film formation. To address this issue, scientists have combined MOFs with polymers to create a new material known as M4. So this combination significantly improves the performance of the material compared to its individual components, making it suitable for integration into various technologies.
Okay, great. And so, yeah, I guess just to clarify there, we have a couple of different acronyms. Now we have our MOFs, which are our metal organic frameworks,
Yeah.
and we have our M4, which is our metal organic framework mixed matrix materials, which are what you're working with in this project.
Yes. So the difference with MOF and M4 is they combine with the polymer to improve their scalability in the industry.
Now, you're only in the very initial stages of this project, so we can't talk much about what you've achieved so far. But, I mean, what are your objectives for this project over the next 2 to 3 years?
In this project, we have 3 main objectives, which we promise to deliver within 2 years. At first, we try to develop a multi-scale computational workflow to predict mechanical properties of M4 from atomic scale to micro scale and verify them with the experiments. After that, these processes will be performed in a high throughput simulation to generate a lot of data sets for our last objective, which is building a statistical machine learning models, correlating the structure and the chemistry, in this case, mechanical properties of M4 composites.
I mean, seems quite ambitious for 2 years.
Yeah, I mean, that was we promised, and I'm in hurry to try to, complete it. But as I say, I got a lot of support from a lot of groups, our group, from local groups. We have all the expert team here. So I believe we can achieve it within 2 years.
Great. And now, just finally, I understand, Phuong, that before coming here to Madrid, you were living in Australia and actually in Canberra, which is where I'm from. A little bit of a coincidence there. But nice to meet another Canberran in this part of the world.
I call it Canberran, yes.
But how are you settling in here in Spain?
My settlement is all right, actually very good. Despite a long distance between Spain and Australia, I found both places have many things in common. Maybe I can say between Madrid and Canberra, like people and weather. So the people in Madrid is very friendly and warm, so I feel like at home. And the weather is also very similar. I live in Canberra, an inland capital city, so we have very dry weather with hot summer, but not too cold winter. So I heard from my local friends that the weather here is very similar to Canberra. But the main difference that I noticed is the language. So even though I have no difficulty to live with only English, but I hope I can take this opportunity to learn some Spanish, which is one of the most popular languages now in the world. So I count it as a bonus.
Perfect. Well, we'll leave it there, Phuong, but thank you very much for your time. And hopefully maybe at some point over the next couple of years, we'll be able to talk again about some of the progress that you're making on the M4 MID project. Now I'm joined by Bruno Gomes, another of IMDEA Materials MSCA postdoctoral fellows. Bruno, thanks for being with us today.
Thank you. Hello, everyone.
Now, Bruno, I wanted to jump straight into the research that you are undertaking here at IMDEA because it's quite a fascinating topic. You are working on the Metal-Leash project, which is to develop metals against leishmaniasis. That's under the direction of Professor Javier Llorca, and I believe you're working as well with Dr. Monica Echeverri Rendon.
That's correct.
First of all, for any listeners who are perhaps unfamiliar with what leishmaniasis is, can you just give us a brief overview to start?
Sure. Leishmaniasis is a disease that is caused by parasites of the Leishmania genus, which are transmitted to humans through the bites of sandflies. Once in the human body, these parasites are taken up by white blood cells, where they can thrive inside the acidic environment that will normally kill other pathogens. In there, they can subvert the function of these cells, which can lead to their symptoms, or they can reproduce, destroying the cell and infecting other white blood cells. The effects can be devastating. This disease can manifest itself in three major forms. We have cutaneous leishmaniasis, which results in lacerations in the skin; mucocutaneous leishmaniasis, which results in the destruction of the mucous membranes of the mouth, nose, and throat, causing severe disfiguration. And we also have, lastly, visceral leishmaniasis, which affects mainly the spleen and liver, and it's fatal in up to 95% of the cases if it is not proper treated.
And do we know what it is about this pathogen that makes it able to survive in environment that would otherwise be hostile to other diseases?
So the parasite can exist in two different forms. In the sandfly, it exists in a form that is called a promastigote, which survives in the same conditions as, for example, bacteria survives. Once they reach the human body and are taken up by the cells, they change their morphology and physiology into the mastigote form and are able to, and especially adapt to a metabolism that is more comfortable with acidic pHs and can deactivate the production of reactive oxygen species and nitric oxygen species that will normally kill other pathogens inside the phagocytic white cells of our blood.
Okay. Now, as I understand it, as I mentioned, a lot of people might not actually be familiar with leishmaniasis, but according to the Center of Disease Control in the United States, there are up to an estimated 1 million new cases of this diagnosed each year, which actually makes it one of their most prevalent neglected tropical diseases. So it's clearly a disease that's having a major effect on many people and many communities all around the world.
For sure. So currently, leishmaniasis is distributed over 98 countries across Asia, Central and South America, and also in some countries in Europe. The risk factors that are related with the occurrence of this disease are usually malnutrition, poor housing conditions, and house of financial resources. So it's more prevalent in the most impoverished zones. And therefore, it is a disease that is considered to be poverty-related. Nevertheless, we have two recent reports from Eurosurveillance from 2012 and 2013 that paint a bit of a different picture regarding the distribution of the disease in Europe. So 2 outbreaks have occurred in Italy, a 3rd outbreak occurred in Spain, and in the end, the report concluded that many clinicians, health officials in Europe, are not aware of the disease, and therefore it is often misdiagnosed. Moreover, the disease is also, even though it's considered a tropical disease in a tropical climate, some cases have also been diagnosed in countries in north of Europe, for example, as the Netherlands, motivated and meaning that the disease was brought there either through migration or through especially tourism. And it concludes that leishmaniasis is a latent public health threat in the EU, and it urges for more prevention and control programs at an European level.
And Bruno, I understand that as well as the physical effects that this disease can have on patients and those who are suffering from leishmaniasis, that there can also be a lot of social effects, social stigma for sufferers as well. Tell me a little bit about that.
Yeah, so as I mentioned before, we have two forms of the disease that are cutaneous and mucocutaneous, which can result in deep scars and also can result in the destruction of the mucosal tissues in mouth and nose and throat, and result in severe disfiguration. So people are branded as having had the disease, and historically there has been some stigmatization and social rejection of these people. That usually in these cases the disease resolves by itself, so the person does not die, but it will have and shown for the rest of our life the effects of the disease. But then, as a result, we have stigmatization, social isolation, which has been known to lead to immense suffering.
Okay. Now, where did your interest as a researcher come from pursuing finding possible treatments for this particular disease?
So this is actually a project that was proposed to me here at IMDEA by Dr. Monica Echeverry-Rendon, which has been working with the disease for more than 6 years. And the more I learned about it, the more interested I became. One of the main reasons is that because, as I said before, it is a disease considered to be poverty-related, and in the most rich countries, even though, as we see, they are also showing some cases the disease is often misdiagnosed. There has not been such a concentrated effort in medical research into this specific topic, as we have seen, for instance, for AIDS, for cancer, or even for COVID-19. Also, because it's poverty-related, most of the pharmaceutical industry doesn't see a potential for a very big economic return or a financial incentive in researching into this. As a result, what we have today for the treatment of this disease are antibiotics that were developed more than 50 years ago, and they are not specific for the treatment of this disease, and can have severe adverse effects in the patients. So as a result, the current treatments are incredibly long and possess variable success rates, either due to dropout or to an early death of the patient.
Now, as we mentioned earlier, the name of the specific research project that you are working on is Metal Leash. Tell us a bit more about this project. What are you planning to do, and what are you hoping to achieve?
So the basic premise of this project is that we can use biodegradable metal nanoparticles, for example, magnesium nanoparticles, which is a material that is known to be biocompatible. And these nanoparticles, due to their small size, can get inside infected white blood cells and reach the parasite, killing it and clearing the infection. As I said before, we have here in that IMDEA Dr. Monica Echeverry-Rendon, which has worked on this project before and has shown some promising results, having shown that there is at least a 50% reduction of the infected immune cells when treated with these types of nanoparticles. So what I'm going to focus on this project is in trying to find a stabilized solution that can be applied, understand how it works, and then maybe move on with final implementation.
I guess it's important here to highlight that the research project that you're doing here is, as you said, building on previous work done here at IMDEA Materials as well.
Yeah, for sure.
Okay, well, thank you very much for speaking with us today, Bruno, and sharing the work that you're doing as a Marie Curie postdoctoral fellow here at IMDEA Materials on the Metal Leash project.
Thank you so much for having me.
Finally, I'm joined by Adrian Boccardo, who is a researcher on the M3TIAM, or multi-scale multi-physics modeling of TI alloy medical implants based on additive manufacturing technology project, under the direction of Dr. Damien Toure, the leader of our modeling and simulation of materials processing research group. Now, let's talk a little bit about this current project that you're working on, which, as I understand, relates to the development of patient-customized bone replacement implants, which is very interesting. Now, your role within that relates to modeling how certain post-processing treatments might affect the microstructure and mechanical properties of these devices. So, first of all, tell me a little bit about the general idea of this M3TIAM project.
Yes. So in general, as you know, it is possible to obtain implants by means of additive manufacturing. So it's a current technology that everybody is trying to use to do this kind of implants. But there are some problems, for example, when we try to build hip implant, for example. That in general the material or the part has some micro defects, for example porosity, and that reduce the fatigue life. And for that reason, after several years, it is necessary to replace the implant. So the surgery is very invasive and there are a lot of problems. For that reason, it was observed that by reducing this kind of porosity, it is possible to increase the life of the implant. Moreover, with the current technology, particularly with selective laser melting technology, the microstructure that we obtain after the building of the part is now under the equilibrium one. For that reason, the material is very fragile. And so by doing this post-heat treatment, it is possible to reduce, at first, the porosity, at second, to obtain a more stable microstructure. And at the end, we are going to improve the mechanical property of the implant. So
let's take a specific example here of somebody who needs a hip replacement.
Yeah.
So I assume the idea would be that you could actually create via additive manufacturing, as you said, or 3D printing, an exact model of the hip replacement that they need, and then to implant that.
Exactly, and our contribution will be in the development of the heat treatment to obtain the proper mechanical property to obtain an implant that can last a lot of years.
Right, very, very interesting. Now, and tell me a little bit about your specific role, which relates to the modeling of how these treatments might affect the microstructure and the mechanical properties. What is your role as a researcher on that?
Yes. So there are different ways to approach this problem. One of them is by using experiment, and the other by using models. So I'm in the second part by using model. And the idea is to develop some models which allow to predict the microstructure evolution during this kind of heat treatment. And basically I'm developing some code, Python code, to model the microstructure evolution. And with that, with the part of the experimental guys, we can in a certain way predict which is the correct parameters to obtain these good implants.
And one thing I would like to ask you additionally regarding this is talking about this M3TIAM project for these replacement implants. Do we have a kind of a time frame of when this project is I believe a 2-year project?
It's a 2-year, yeah.
Do you have any kind of time frame of when this technology that's being developed might be accessible for patients in use in the healthcare system?
Okay, now I'm going to give you my personal opinion, not my professional one.
Okay.
I think that 5-10 years could be something reasonable. You know, the development of the technology and moving that to a company, to industry, takes a lot of time. There are a lot of regulation that this new kind of implant need to fulfill, hours of test and so on. So 10 years could be something optimistic, but I think that the quality of life will be increased a lot. So.
Well, I guess in the scale of this kind of research, 5 to 10 years is the very near future. Yeah. No?
Yes, I'm a little optimistic because the additive manufacturing technique is on the street, and also some of the numerical or computational technique that we are using are something very standard. So we need to put these two big parts together. So it's something like that. For that reason, I think that we have two major technologies and we need to put together. So
great. Okay. Well, thank you very much, Adrian, for speaking with me today. Best of luck with the project, and hopefully we might be able to speak again at some point in the future about some of the progress that you're making.
Okay. Thank you, and very nice to talk with you.
And you. Well, that's all we have time for here. I'd like to thank my guests once more, Phuong Vo, Bruno Gomes, and Adrian Boccardo for joining me today. And don't forget to check in the same time next month for the next edition of Discover Materials Science with IMDEA Materials Institute. I am Andrew Johnston. Bye for now.